Hey everyone, welcome to the 14th episode of Coffee with Cosmos DB series. If you're joining this series live for the first time, please make sure to subscribe the channel. And also, if you have missed to watch the previous sessions, you can watch it under the playlist that we have, as it has Azure Cosmos DB Coffee with Cosmos DB series. You can see it on the right side. And if you have any feedbacks or if you want to know about a particular feature or any use cases, you can write it as a comment on the chat. We will take it up in the next upcoming sessions. Yeah, with that, we can get started with our session today. We have a special guest. I think he's joining for the second time. Probably he might not need an introduction. Let me add him to the screen. Here's Subhashish.
Yeah, hi Saji. It's a
How are you doing?
pleasure. Yeah, it's a pleasure to be on your show. I hope I'm audible,
Sure.
right?
Yeah, I can hear you.
Yeah, thanks.
Yeah, thanks for joining. So probably you might have already introduced in the previous discussion that we had, but
Right.
you can go once again for the new joinees who are watching this session. Yeah.
Yeah, sure. Thanks. Thank you, Saji. So I'm basically Subhashish. I'm a cloud solution architect, data analytics at Microsoft. And at Microsoft, I mainly focus on some of our large global, you may say, retail consumers, and definitely, focus on Azure Cosmos DB.
Thanks. Yeah, today's topic is much interesting to, I think, all the distributed data customers or who are using databases which are distributed, right? And it's about partitioning. And I think when we talk to customers or even developers, the fundamental thing that we start with is partitioning. So it's going to be an interesting session. Yeah, we can kickstart, Subhashish. So if you have any slides, let me add them to the screen as well. Yeah, you can go ahead.
Yeah, it's visible, right?
Yep.
Yeah, thank you. Thanks. Yeah, and absolutely, as you rightly articulated, right? Partitioning is not only one of the fundamental concepts, but also definitely one of my favorite topics when it comes to Azure Cosmos DB. So we'll definitely focus on partitioning for this particular session. So today's agenda, how it's kind of broken down is basically we'll talk about what is partitioning, why is it like required, and definitely we'll talk about some of the basic foundational concepts like logical and physical partitions, which are very important to understand. This is directly ties in into some basic fundamental understanding of like what hashing is, the different kinds of hashing, and what basically Cosmos DB uses under the hood when you create a partition key, which then kinds of ties up with some design goals as a developer or an architect, right? You are architecting a particular use case. So how do you choose a partition key? Are there certain best practices around it? Knowing those are very vital, because this is possibly the most important design choice that you will make in your application, correct? Then we have different kinds of partition keys. What are the different ways to look at it? And what we will do is also we'll quickly take a look at two different use cases, so that the concept that you kind of understand or learn here, you can apply them, right? And kind of understand how we are taking different decision-making calls. So let's go ahead with it, right? I mean, so when you're talking about partitioning, right, before we talk about like what exactly and how we are exactly doing it, the very fundamental question that people often have is why do we need it? Or why does any of the distributed NoSQL databases have partitioning as a cornerstone concept? Technically, why do we need it, right? So the single word answer for this is owing to the requirement of what we call providing scale. So now in terms of specifically tying that with Azure Cosmos DB, right? So when we work and architect different cloud native, what we call modern workloads, right? Or use cases like it could be, think of a big data IoT analytics case you are building, or in retail specifically, we build a lot of fraud analytics use cases. We do recommendation engines, right? All of this data, which is associated with these workloads or use cases, we'll see they are quite in the nature of big data. You're talking about terabytes, petabytes of data. Most of the applications, for example, some of the large retail customers, you're talking about 10, 20, 50 terabytes of data on which all of these have to kind of, transaction are captured and then processed, and then, downstream applications kind of consume it. So what happens is I cannot fit this amount of data on one machine. So you have to technically, scale that one machine to dozens of machines, right? That then becomes a pretty complex task to do. And even if you scale that one particular machine to dozens of machines, the question comes up is how do you distribute this data, then write it, then basically read it, right? So these are a couple of fundamental, problems to solve in distributed databases. Now, what Cosmos DB basically does is we basically do horizontal scale out, which means all of our data, we take it, we distribute it into a number of smaller machines, right? And then each machine is responsible for storing a subset of the cumulative data. And vitally, again, very important, as it says, right, you only pay for the throughput and the storage you need. Hence, this is referred to as what we call the elastic scale for both the throughput and the storage. So now, if I tie this entire concept, right, with partitioning, why it becomes important? Because under the hood, Cosmos DB uses basically, partitioning to scale those individual containers, those collections in a database, right? So that we meet the performance needs of the different use cases of the applications that you're building. That's the fundamental. Now let's look at two very foundational concepts. If you're a developer or an architect, right, you have to understand this, pretty clearly. So as I mentioned in my previous slide, right, that Cosmos DB uses the concept of partitioning. Now, I'm scaling basically what the individual containers, the collections in a database. Now, what happens is basically the items residing within the container, the collection, right? They are divided into what we call distinct subsections. Those are what is referred to as the logical partitions. So logical partitions are nothing but they are formed based on the value of the partition key. And we'll look at what exactly partition key is in the subsequent slides that you select, and then they're scoped together. So logical partition stores all the data associated with a particular partition key value. That's very important. So, for a developer, when you write queries, when you retrieve the data via queries, right, basically, or insert data. So all of these database objects, including even the stored procs, the triggers, the UDFs that you create, they are all scoped to this logical partition of the collection. That's a very important concept to understand. On the other hand, we have physical partitions. In the simplest sense, you can think of a physical partition as like, I have basically a piece of hardware with an element of compute. It definitely has an element of storage also. It's basically a type of what we call, as you see on the screen, it's a reserved SSD, like batch storage. So one very important point to note here is, there are 3 points to kind of remember here. That is, and I have, as mentioned on the screen, like segregated them as an implementation perspective, as a developer perspective, as an architect perspective. From the implementation perspective, remember that you don't have to create the physical partitions. It's Microsoft's and the Azure Cosmos DB engineering team's kind of duty and responsibility to distribute basically, the physical partitions and handling of the physical partition, which is an implementation detail. But the other hand, the logical partition, of course, because it stores all data associated with the same partition key value, so that defines that the partition key choice definitely lies with the end user or the developer. For a developer, again, very important, you basically define one partition key per container or collection. And remember that all objects are scoped to that particular logical partition. From an architect perspective, it's good to always know that a physical partition has 2 boundaries. What is that? That basically I have a 50 GB storage and a total throughput support of 10,000 RUs for a physical partition. And also very important point to remember, because this will play a vital role in the choice of our partition key later on, is I have a 20 GB limit on the size limit on the logical partition as well. So this, if you're an architect architecting a certain use case, these are certain good points to remember. And also there's a particular link given there. You should visit that particular link, for more details actually. So these are 2 very fundamental but very important concepts. Logical partition, which stores all data associated with the partition key value, and physical partition, which is a fixed amount of reserved SSD storage plus compute. Now going ahead, right, what I'll quickly do is I will stop sharing my screen. I will quickly, can you see my correct screen right now? I have, no, this one, correct? Can you see my Azure portal right now?
Yeah, we can see it.
Correct. So basically, let's take a look at quickly how to know it. So I have a account where I have a couple of databases. I go to nutrition database. I have a collection called food collection, and scale and settings, right? It's a perfect place where you basically check the partition key value. So for example, here the food group is the partition key value. A fundamental question is, this basically scopes for me the logical partitions. But can I see basically the physical partition layout for this particular collection? Often people ask. It's possible. There are multiple ways to look at it. So quickly, let's take a look at. So you can go to home. Basically, you can fire a new SQL query. And if you fire this particular query, right, and let it to run to execution, it's basically a full partition scan, or basically you can say a full table scan. Once it kind of executes, you can go to query status. And if you see query stats, basically per partition query metrics.csv, it shows you a particular file. So that particular file, if you open up, It's very important because it kind of gives you the breakup of the partition key range. And we'll talk about these, what these two terms also mean. So if you see on the screen, the 0 and the 1. So these are two different physical partitions. So that means basically two physical partitions make up the particular collection of the container on which you are executing the data. There's another way to look at it. The other way to look at it, which you should be aware of, is you can definitely go to insights. Within the particular insights, let's say you take the last 7 days, you can choose from here the particular database that you want. You can just choose the container, the food collection. In the second tab, this is a very, very important tab, is throughput. In this particular throughput tab, if you just scroll down, this normalized RU consumption by database. This is a very important parameter. It basically gives you a breakup of the physical partitions. And if you just kind of scroll down a little bit, it gives you a heat map of that particular partition key range ID. And this gives you the breakup of the physical partitions that exists within the container, and also gives you a approximate overview of the utilization of the throughput and storage for that particular physical partitions. For example, and this is good, though it's beyond the scope of our discussion today, like if you want to identify hotspots in your application, this is a good place to do so. As you see for mine, it's 29%, 26%. If one was like reaching 100%, the other is very underutilized, let's say 10%. That means I have chosen a wrong or an incorrect partition key for that particular querying that I'm doing in that particular container. And I have a hotspot. That means I have one particular partition which is overutilized and one particular partition, let's say, possible to be underutilized. In such a case, you should look at repartitioning or kind of creating a new container, basically, looking at different other design principles. But in my case, as you see, it's pretty fairly equal distribution. So I'm good. So normalized RU consumption is also a place where you can come and see the partition key range IDs, which kind of tells you the physical partitions and their particular IDs. So this is something which I really wanted to kind of show. Now I will go back to my other screen, which is correct, this one. I hope it's visible. Correct?
Yep. Probably you
Yeah.
need to. Okay.
Yeah. So I will. Yeah. So that's it. So basically, by now quickly tying this into a quick introduction to hashing. This is very important to understand fundamentally like how the partitioning works under the hood. So and also it's very important to understand this. Why? Because it provides a deterministic, and we will see a consistent manner of baking in scalability. Because in a distributed system, it's not just about scale, but how do you also consistently handle your queries when they come up, right? So it's very important. So it's a vast topic. We'll just cover some of the basic things. So a hash function, in a very simply put language, is basically a function which uses to kind of map data of arbitrary size to any fixed size values. And although there are some hash functions, that suppose variable lengths, but we'll keep it very simple. For example, here you see that maps basically a function maps names into different integer values. Now earlier, right, we basically spoke about physical partitions and logical partitions. So coming to a physical partition, right, the thing to note about a physical partition is that it's actually not one server, but mathematically, if you represent, right, it's basically what we call a set of servers from 1 to infinity. So there is a point to note here, is very important, is that within the partition set or the physical partitions, we actually create something what we call replicas. So what we do is when we create a set per region, right? Let's say you have a multi-region deployment like this. So what we do under the scenes is within those physical partitions, what we're doing is basically set up database replicas where we host the Cosmos DB software itself, right? And then we distribute this workload across many, many replicas. So in usually a region, you have a quorum of 4 replicas that we call it. So you have a 1 primary, 2 secondaries, and 1 forwarder. Now let's say they are marked red and green, as you see. So let's say I have a region wherein I'm kind of writing red piece of data, and another set of region wherein I'm writing green piece of data, right? And I have a massive distribution of data. So I basically split this across terabytes of data. So I split this efficiently into smaller chunks. So one important question or a problem that comes up here is, let's say I have a request which I want to kind of route to the red, another request to read basically the green. So how will the Cosmos DB, basically the engine, know, kind of to go precisely to a region where to find the red and precisely the region to find the green. Now this basically becomes very important because as you see on the screen, right, request 1 is to read green and the request 2 is to read red, right? So I need to deterministically kind of send it, and also while retrieving and writing back, it also should either retrieve or update or write back from the same region. So I should have a situation also where I have consistent read-write ability. So these two properties, determinism and consistency, are very vital, and they were for preserving basically what we call the integrity of the reads and writes of a database. So a very important concept associated with this, classically was what we used to have, or a concept called naive hashing. That means I take a particular, hashing function. So this is the hash part of the hashing function, which is represented, right? And basically it's represented as a single line, like 0 to max value it has. And let's have different data points which come in. Let's say I have 5 data points: Subhashish, Abhijit, Tom, Dharmendra, and Pradeep, and write them at different points of this particular hash line, right? So if I look at a naive hash of those values, let's say top 3, Subhashish, Abhijit, and let's say Dharmendra, right? So what happens on the naive side is, let us say I do a hash of some number, and we are basically doing a mod to find the number of partitions. So it's basically nothing but a modulus operator of a number of a partition. Let's say I start with 2, so I can distribute these 3 as 1 1 1 2, and another one maybe 2 1. But what happens if the data grows? I add 2 more names to it. So you will see now I have to move 1 to another. Maybe it stays on the same physical partition. 2 stays on the same. The third one has to be created to 1. So I have to move the third one to the second one. The second one I have to move it to the last. So there's a couple of movements involved. So if I do a random distribution of values, you will notice there is a lot of kind of wastage in movement here. Hence, no distributed basically database uses this concept of naive hashing anymore. Otherwise, the concept stands good. So what in Azure Cosmos DB we have done is basically we have taken this concept, but we have kind of modified it into what we call the consistent hashing. And then, of course, one of our innovations is we have done something called range partitioning on top. So ideally, what this means is basically, we take a hash key space, and then, what we, instead of representing that hash space as a straight line, what we have done is basically represented it as a wall clock, you may say. So basically, it's like a pizza, you may think. And as shown on the screen, right? So you have a min value, it kind of rotates and goes to the max value and kind of rolls over to the min value. So given the hashed values, right, as you can see, right, let's say I have Bob and Danny on 2 different sides, and I've distributed Carol and Alice on the other side. Let's say I have a requirement of this particular computer to be split. So what I can do is I can initiate a split in between and kind of split them into 2 different M1 and M2, basically partitions. So they become, ideally speaking, 2 different computers for me with, storage and, space you may think of. Let's say now my data points have grown, Carol has grown or Alice has grown to a much larger part. So, I can, as the second image, as you can see, I can split maybe M2 into M2A and M2B. So, I can have an M1A and M1B and so on. And let's say I have now 1 million data points specifically for M1A or M2A. I can further split it into M2A dash, M2A dash 2 dash 3 like this, and, basically keep on splitting. So we have a very deterministic way. Now, one important point to know is that there are a couple of points, associated with it. One is that a partition can split itself in isolation and elastically grow. Now, that is a very, very important concept. And then second is, we have this gives us an ability to kind of what we call deterministically also way of locating this information. And how do we do that? And that's how, when we will talk about in the partition key choices later on, right, we'll look at the simple, the synthetic, and the hierarchical partition keys. That is, what happens is, if I hash a value later on when I want to query it, right, let's say for Alice's information, let's say I hash Alice and let's say I get a number. Let's think about imaginary number 1 2 3 4. And then when we take a look at this ring, so let's say we will go from 0 range to a particular n range. We will try to take a look at that. So from 0 to the n range of this particular partition key range, right? We'll look at, if we not find this data here, we'll go to the next partition key range. Let's say we'll go from M to K and so on. So we know precisely which range to go to. And you will find that this particular information, that is hash of that 1 2 3 4 number or 1 3 5 6 number, it will tie into a specific partition between M to K, let's assume. So then what I can tell Cosmos DB engine is basically route my queries to a specific partition and do not search for the others. So what happens, this particular hash value then technically becomes what we call in database terminology, right, a placement hint. So my partition key is nothing but a placement hint for that particular query to go and look up for a particular physical partition in the layout table actually. So that's how it basically works under the hood. So in summary, like to summarize this particular slide, like when you fire a CRUD call from the SDK, like this placement hint of this partition key value is essentially, it tells the Azure Cosmos DB service to route the writes as well as the reads to the correct computer. So this is a very important concept. So we'll pause and take any questions, Saji, if you have.
Yeah, let me see if there are any questions on the chat. Okay, I think we have one question from the audience. So it's a fundamental question he has mentioned, and the question is about if we want to change the partition key after some time, realizing that he has not done the modeling right, how that can be done.
So right now, see, if you have a particular use case and you eventually want to move to another particular use case, let's say it has changed from a read write to read only, and you want to fundamentally change the partition key, you can redesign it, but you can't do it on the fly because your queries will get impacted and also the container will get impacted. So as of now, I mean, that dynamic ability possibly will someday come. But right now you have to create a fresh container with a fresh partition key choice. And there are multiple ways, you can do an intra container copy, or you can just copy it if you don't have much data, you can directly move that data to the new container.
Got it. Okay. I think that answers his question. I have one question. So you mentioned that
Yeah,
Cosmos DB uses hashing function, right, to find the hash
correct,
value of what we are use as a partition key.
correct.
So to be clear, which part of this implementation detail and which part is user generated?
Yeah, good question. So, Saji will also definitely look at this in the subsequent slides. So, the choice of the partition key lies with the developer or the architect. So, that's an end user choice. Definitely passing the value to that partition key also lies with the end user. For example, in the demo which I showed, so food group is the partition key. So that is choice of a architect or developer based on his query pattern. What food group value is takes, let's say in a query I fire baby foods. That is also choice of the developer. But the hashing value, the hash function, the management of the physical partitions and the splits also if it's required, those, as a developer, we should not be bothered about because those are part of the managed service by Microsoft.
Yeah,
Those are all implementation details taken care by Microsoft.
got it. Okay. And is the output of the hash function is always a single value, or can we have more than one output value? I mean,
Yeah, that's also a good point. So again, we'll take a look at that also in subsequent slides. So the
oh,
answer
okay,
is no, it
got it.
can be a more, a composite value actually. And that's where we have done all the innovations around giving you more scale even within a particular container, right? So the answer is we can have multiple values.
Got it. Okay. I will allow you to proceed with the next slide, so that will give us more detail.
Yeah, definitely, Saji. So we will proceed. And this kind of ties into our next, section, which is what are the design goals? What are the basic practices I should know while choosing a partition key? Very fundamental choice always is when you're talking or as an architect or as a developer sitting down or adopting or thinking of maybe adopting Azure Cosmos DB is to understand your use case. That never goes away. And in that particular use case, the first question that you should ask yourself is my use case read heavy in nature versus write heavy? Now, at times, like 60% or 75% of the times, you will see that you are able to take a call. There are certain retail scenarios, like people are reading comments. If there are 1,000 comments, people usually read quite a bit. They don't write that much. You have retail analytics, where the total number of cumulative reads is greater than writes. So that's a read heavy workload. There are ways to choose a partition key and optimize for the same. That is something which we should be aware of. On the other hand, in the end of the spectrum, there are certain which are clear cut. There's a distinction that they are supremely heavy in writes. IoT, all use cases are very high write intensive. So if you have a use case like this, then definitely there are certain practices which we'll cover now. You should keep in mind. Now, having said this, there are certain use cases I've come across where it's a 50-50 split. So there, of course, you have to optimize for both reads and writes. You have to take a best judgment call or use something like hierarchical partition key, which we'll talk about in the few, in a couple of subsequent slides. Or what we always tell people is take a judgment call on what the use case predominantly kind of optimizes for. If it's read and write equivalent, but it is optimized for read because that bit of it is very important for the business, for the SLA, for the performance, for the price, for the cost, then you should go for definitely the read heavy intensive kind of a scenario case. And so these are different calls which you need to take while designing. Now there's basically a summary or certain best practices that is presented on the screen, you will see, and there's an associated best practices documentation. A link is there, which you should definitely visit and take a look if you're a developer and architect. The golden principle, like if you have to summarize this entire slide, the golden principle to follow is a very simple rule, that is the choice of your partition key should suffice for a high cardinality. So what that means is the cardinality of a logical partition, right, is basically becomes what we call the scalability bounds for your Azure Cosmos DB. So higher the scale you want for that particular given use case. So let's say I'm building a use case for 100,000 people. That scale is very different from when I'm building a application which will scale to 15 million people, which is very different from scale. If I say I'm building the next Facebook, Snapchat, Instagram, you're talking about potential 8 billion users, right? So your scale bound is directly tied to what we call the cardinality of your partition key. So that's a golden principle to follow, that choose it in such a way that you have upper higher bounds, you have very high cardinality. So rule one is basically know your ballpark, of your scale needs. This right now what I told. So when I sit down with developers, architects, it's a good fundamental question to ask. Maybe at times you're not aware of, you should then take a higher ballpark in the frame of some good request per second or TPS, and architect backwards from it, do reverse engineering. Rule two is having a good understanding of the workload. First is the scale bit of it. Second is how do I do the writes? How do I do the reads? Is it a read heavy versus write heavy? What we mentioned, right? So it does not need to be precise to start with. Very important, but very important to know is having an idea of what we call the order of magnitude. That becomes very vital, because there is a difference between 10 requests per second versus 10,000 requests per second. There is not much difference between 3,000 and 4,000. So the order of magnitude is very important to kind of architect or write down or calculate. Rule three, very important, is once you do have an idea of the use case, of the workload, of the scale, then you better start drilling down. So what I do when I work with a lot of tier zero application teams, I sit down with them, understand the query patterns. It's a good practice to do before you have even done anything, because in Cosmos, the core utilization happens and the best utilization happens when you do the CQRS kind of a pattern, right? And the fundamental CQRS is knowing your reads, writes, and then being able to kind of differentiate them, right? So very important is you take your top 25 queries or top 5 queries, you drill down, you look at what's the most common predicate filter. Are there certain edge cases? Very, very important. Sometimes it happens the edge cases become very vital for a given use case. So how do you factor those in? So those are some of the important points you should know. But then again, for a very important point also to know is we will definitely talk about distributing the overall request and the partition key scope. But one general tip to follow is, which I have often come across, is, hey, you know what, I'm building a highly distributed application, but let's say I end up with a lot of logical partitions. Is that bad? A very, very, very important but very fundamental question. The answer is no, it's not bad, because people often tend to worry. But if I have billion of partition key values, will I run into any scale problem, any issues in scale, or any issues in computational power? The concrete answer to this is no, because at the end of the day, right, the number of physical partition sets, that's always bound by the number of logical partition keys you define. So what that means is basically, if you have a total of one partition key value, right, we can at the most distribute this only under one underlying physical partition. So you're always having very low scope. But on the other hand, if you have one where you have billions of partition key values, so we have different ways to look at it. We'll not cover it in this session today, but we have an underlying concept of co-location, right, where we co-locate a smaller number of underlying physical partition sets. Let's say starting with number one, then we can grow it to an ever increasing number of physical partitions, and such way that I can have billions of keys and I can grow it to billions of underlying partition sets. So scale is never a problem if you choose your logical partition key value correctly. That's the important thing. The underlying physical partitions Microsoft will manage for you. So choosing the right key becomes very important. So if I kind of go into depth between the two design goals, one is the top design goal, which we call is you have to be able to choose a partition key in such a sense that you are in a stage where you distribute the overall request and the storage volume. So this is what prevents you from having hot partition keys. That means overutilize couple of partitions and underutilize a couple of partitions. That is a bad position to be in. So what basically this means is, I need to choose a partition key where I kind of distribute both my overall requests and being able to distribute the data also, in equivalent fashion. So let's say I can able to Let's take a particular example. Let's say I have an IoT telemetry store. So I can have many devices. I can have millions of devices writing into a database. So this is essentially what a write heavy database, right? And let's say I choose a particular partition key, which is, let's say, time, and that's a good practice. Also, you write down maybe a future perspective JSON document structure, and you kind of check the different properties available, and then you kind of debate and judge. We'll see that in the use case also. Let's say I take time, or device ID, let's say. There's nothing wrong with it, but if I take current time, but what will happen is when I try to query it across a particular device, for that given time, all of this will kind of land into one logical partition. That's basically a bad design choice, right? What about device ID? Again, not bad, but definitely device IDs will have multiple. If you have device IDs, right, I will have multiple equally distributed let's say logical partitions. But then very important points is here a synthetic key. That is, if I introduce high cardinality, let's say I take the device ID plus the current time, that's also a good point which we can take a look at, right? So the fundamental here, the point to understand here, you should choose a partition key that effectively load balances your request in any given point in time. So that's the fundamental point that we should always keep it in mind. Now, which kind of then brings me or us to a partition key choice, which is again one of the fundamental questions that often I get into discussions with developers is there are multiple types of partition key choice. Which is what and which one should we use at what situation? So as you see, right, a simple partition key is nothing but which has a single value. And as we mentioned, you can optimize it for a read. If it's a read, then please go for the most commonly picked predicate filter. That usually becomes your most common simple let's say partition key choice. If it's a write, there are multiple ways to optimize for it, but then you should purely focus on cardinality, because their purpose is, I have a very high write heavy workload, right? I should be able to write it fast enough to do maybe some subsequent downstream operations. Now, let's say I have given some sample C# code, like I have a nutrition database, I have a food collection container, which we saw, right? And let's say I'm doing a point read or a point lookup. So I'm using the read item async function, basically method, which acts as an object like serializer, deserializer. And then I pass the item ID, plus you will see the very important, the partition key value. So for us, for example, it's the food, baby foods in this particular case. So this is an example of a simple partition key. You follow the simple rule, simple principle, and kind of come up with a single partition key value. But there are certain cases where this may not suffice, because you're trying to balance between read and writes, or you're write heavy in nature. So you need to have high cardinality in the system. So then what we do, or we suggest you do from an application user perspective, is basically do a concatenation of multiple properties. It can be a concatenation of 2 properties, 3 properties. I've worked on 4, even 5 properties. You can kind of write down the JSON document, you concatenate, and you come up with something unique. For example, here, as I've mentioned, like there are 3 types we have seen. You can do one where you just add the 2 and concatenate and come up with a composite or a synthetic partition key. Or you can always do certain use cases where, kind of you do a random, add of a number generator as a suffix to that particular, property value. Let's say you don't have others which you can join. Or you can also do an algorithmic, generation of a particular parameter value. This is very useful in certain retail cases I worked on, where it's not just the ability to randomly generate. At a certain instant of time in queries, they had certain queries where particular number I should be able to pick up and kind of quickly search, because the biggest problem with random generated numbers is they're easy to write in, they're difficult to query from. So if you have a algorithmic way of creating a suffix but high cardinality generation and then concatenate it with an existing property, then the way the hash function works, right, behind the scenes, of course, is we have a way to kind of tell you exactly and retrieve it. So the retrieval becomes much faster than just having a random number generator. For example, the example which is given here, the device ID and the date, you have created a partition key basically with the concatenation of the 2. That's a good thing to look at for increasing cardinality. The very important third point, which we are seeing pretty good use cases in certain specific use cases. If you have a multi-tenancy SaaS, you have a retail scenario, you should look at something which went GA on 23rd of May. That is a hierarchical partition key. So in a hierarchical partition key, what happens is we're basically doing a listing of the partition keys in hierarchical order. As of now, 3 different stages or levels is supported, or what we call levels of key. And what we get is we basically get a reference to the database that the container will be created in, right? And then we create a container which is then sub-partitioned by that. So for example, in our case, we have taken the tenant ID, a user ID, The third one could be, let's say, a particular event I'm looking at or a subscription I'm looking at, right? So I can create 3 different levels of branches. So what this gives me is basically, and we will talk about it later on in one of the use cases examples, is gives me first of all an ability to scope it better. If I have a multi-tenant SaaS kind of an application where I have the requirement of not just scoping at the top level but at the second level, it naturally fits into a hierarchical type of patterns. That's the second benefit. Third, also, for the first simple and the synthetic, I have as we mentioned, the logical partition key value limit. The boundary is 20 GB. What if I'm reaching to that limits? So hierarchical partition key is then a perfect way to overcome that particular limit, because now I have more higher, margin or a playground to play with. So that's definitely another third use case you should be remembering. And fourth is there are certain use cases for which you have querying patterns in which you may want to query for not just the primary partition key value but also the secondary partition key value. So you can then mention it in a query in such a way that both of them get mentioned. Then it's a fully 100% in partition query. So there are certain use cases which are very good for hierarchical partition keys. So that's also a third point that kind of choice you have. So again, based on your use case, based on the workload nature, based on your TPS, which is designed as what's the volume you're handling at scale, you should make this choice. Should I go for a simple partition key? That means partition key as a single value. Should I concatenate different properties? Again, based on your use case, different properties come into play based on your query retrieval. Or should I kind of architect such that I have a hierarchical partition key? And we have a couple of good sessions on YouTube wherein Mark Brown covered this in depth. And there's also a blog post and associated document, right, for choices to make. I continue. Yeah, so thanks. So basically, the second bit of it is, what we call the connectivity in terms of granularly kind of looking at the levels, right, of your partitions, so that you have more amount of like partition keys, which gives you the more scalability to and being able to kind of granularly looking at the and minimizing cross partition requests. So this is something which is also very important and good to look at. Hang on, so we will proceed to the next slide. Yeah, so we'll wait for any questions, Saji. If not, we can look at the two scenarios.
Yeah, there are a couple of questions on the chat.
Oh, yes, please. Sorry. Yes, please.
The first one is from Swarnajit. I have one small question. How do we avoid hot partitioning if I don't want to increase my RUs? What's the workaround to avoid that?
See, again, best ways to like do all of the steps that we told is basically scope it better. Hot partition arises when you have a scenario where you are definitely doing queries on one particular physical partition, the others are lying idle. And that usually happens when there is a flaw in design, right? That means that you did not kind of scope it correctly, or the scoping method was not correct, or maybe you scoped it initially correctly, and the use case has changed. So understanding that what type of use case it is, what is the volume, what's the TPS, and then also read write. And if you can write down the different queries and basically come to the most commonly used predicate filter, it should solve your problem. Yeah, if you have a certain TPS requirement very specific to your use case, there are certain edge cases where whether you should go for a synthetic key or can I go to maybe a hierarchical key, which kind of solves my 429 problem, like throttling problem. Those are very edge cases details. But the fundamental question is to be able to scope, technically scope the workload. That's like fundamental, very important.
Got it. Okay. Yeah, I think you have already shared some of the steps that customers need to be aware about. Yeah. There is another question. I'm not sure if it's relevant to the session, but it looks like why Cosmos DB has so many confusing features such as hierarchical partition keys, partition merge, burst capacity. It looks like all of them are solving the same problem. Why can't we make it easier to customers?
So question is very good, but I take it from another perspective. Rather, it's very features rich in nature because each of them solves or tackles a very precise problem. Like, for example, burst does something very else. Maybe it's outside our scope of our discussion, which is very different from hierarchical partition keys. Again, hierarchical partition keys, which we'll cover in the use case example later on, right? You will see it solves a very specific need of certain use cases. Can I do that with auto scaling, which is a different feature? No. Can I solve it with a burst? No. Can I do it with auto partitioning or some of the new features which are getting, kind of released right now in private preview, public preview? You will see, no, they solve a different set of problems. But end of the day, how I have seen, if you have a very specific use case in NoSQL or in the SQL world for PostgreSQL, right, which has a very typical, use case scenario, you can fine tune your Cosmos specifically for that need. That's why these features exist, right? I mean, that's how I would look at it.
Got it. Okay. We have one more question. Maybe we can take it at the end once you show the scenarios. Yep.
Correct. So I can proceed, right?
Yep. Go ahead.
Yeah. So yeah, you can see two scenarios that slide.
That's right.
Yeah. So basically, the first one is a very simple one, but pretty difficult to architect and come up with a scenario. Is where I have a multiplayer gaming scenario. So let's say next game is Walking Dead, right? It went like live in 2018. I think it's considered one of the most used multiplayer like games in the world. So it can support up to a few billion users, right? And then these players could be present in more than 1,000, gaming sessions. So what you are trying to think of is a game session is technically a primary entity here, correct? So I have a get games by ID. I mean, if I to approach it as a developer, the first point from the business perspective is I would scope it to what's my most commonly asked queries or questions. Are they aggregates? Are they individual game details? Are they details not of the games but of the users only? So or are they of different functionality like add game, remove game? So these are something like I would list them down. That's a good practice. Let's say that I would definitely work with one of the teams to come up with a simplified version of what a JSON document with the different properties look like in a game. What are the top 10, what are the top 15 properties which defines that particular game session for me? So let's say it stores information like who is the player, what is he playing at a given instant of time, what's his score. In a score, let's say, is it related to a leader dashboard? Then do I have a start and a stop time? What are the different operations I need to do on top of it? Then is this game player playing in multiple other games? Is he just playing singly, or does he have a different partners in different games and play as a joint team, right? And then let's say I have questions like get me all sessions of the game. So what is the choice of a correct partition key? Now, there is no right and wrong answer. This is a good point to kind of take a look at and go back and kind of discuss in depth and look and come up with different business uses around it. So as you see, right, you can produce two choices. So either a player name or by a game name. So you have to define here in a case like this, which is very muddled. You should quickly come to what's my primary entity here. Now, important points, a couple of important points here, right? From a design perspective, there is no right or there is never a one-shot correct answer. So it's never like this, that this is right and that is wrong. What basically it depends on the use case, depends on the query context. So what you should look at is after you've discussed the typical, nature, the scenarios, the entity details, you should see and try and understand or try and scope correctly, which ties up into the question the gentleman asked earlier, like I've run into a hot partition, what should I do? Same operation there. You have to look at the use case and the query context. What that means is, what is that operational functionality I am optimizing for, or my given use case is optimized for? So which basically means that if I know the key operations, how are these operations kind of distributed? Let's say I have a large set of data wherein my key operations here would be, let's say get me, the query would be like all game sessions, but for a specific player. Then choosing a player ID is perfect. Why? Because my data will be skewed towards the individual players, correct? But we don't have an index on game ID, let's say. But let's say your 80 or 90% queries will be then single partition query. If I scope it to player ID, definitely there'll be a 10 or a 20 or a 15% which will be cross partition queries where I have data not related to a player. It's okay. There's nothing wrong with it, right? But let's say I have a scenario, right, where I am basically querying on games, where I have specifically only looking for different features along the game. What's the most commonly played game? Specifically game-related details and storing them. Possibly the game ID would be the correct choice and not the player ID. That's an important decision. There could be a place where I have a mix of 50-50. That preferably then I can store two pivots of the same data. That's also a CQRS pattern you can definitely do. I can store maybe in two different containers. correct? I have a player ID container and I have a game ID, and I precisely partition the data in such a way that I optimize queries for that CQRS pattern for specifically a player ID and a game ID. That's also not a bad concept. Definitely, again, you should look at scale and the cost associated to it. But essentially, if you have a scenario wherein you have an equal distribution of the two, then you have another choice of maybe choosing the game ID as the partition key. So there are multiple ways to look at it, right? But then again, maybe for this particular case, it would not be so simple because gaming is a real-time operation, right? So in part of this discussion, right, definitely TPS would come into play. That's what's my transactions per sec. How do you define that? What's the SLA for those? What's my read-write SLA? So can I get a latency when I do a get within a partition for less than 10 milliseconds? That's a very important question. So you will find even those answers or those answers to those questions would define your data model choice often. It's not just the forward one, the reverse engineering also becomes very vital. Because here it may be possible that for certain use cases, though that 20% of the query, which is not, let's say, partition key, I take a player ID, but my gaming details I'm extracting, but those are such some millisecond level or 10 millisecond, 5 millisecond level queries at very high TPS I need to optimize for. It's better than to create maybe a new container with that particular partition key and scope those queries there. So CQRS in such scenarios where it's high volume, low burst, real-time scenarios, your partition key choice is possibly the most important design choice. We spend a lot of good time on use cases like this. And the second one is the multi-tenant scenario. Again, very typical, right, in retail. You have a multi-tenant SaaS, you're trying to, let's say, log in kind of event information, right? You have 10,000 event tenants, and each tenant, let's say, has 100,000, or let's take it even higher, 10,000, 100,000 users. So what happens is, you note down in these cases, again, you sit down with the team, you understand the data access patterns. So what's my read operation? Can you get all data for a specific tenant? Can I get all data for a specific user within the tenant? And then also you see the write operations. Can I insert data for a given tenant? So what's a good choice of a partition key here? Now, this is a good problem to solve and look at. The obvious thought would be that, why don't I take, and of course, we've created a JSON document with the data, right? You have ID, tenant ID, the event type, and all of that. So your choice would be like, why can't I just take a simple, partition key over a single value key that is a tenant ID? Now, there's nothing wrong with it, but the problem is when we partition by tenant ID, the queries for a tenant or a user, they're very efficient, correct? They are scoped to a single, partition query. Behind the scenes, what we are doing is basically we are doing a hash of the tenant ID. So if you see the first line in the blue box, right? So your placement hint ideally becomes the hash of the tenant ID. But the problem is you have a SaaS and you have multiple tenants, right? And what happens if the single tenant grows large? So then your problem will be, but on your logical partition, right? I have a 20 GB storage limit for that logical partition. So this partition key strategy is good to start with, but you will find you will run into issues of scale, problems, cost. Once the tenants, some of the tenants may have more requests than the others. So this can lead to what we call the hot partition scenario. So it's a good key to start off with possibly, but not a highly scalable model. So we should definitely take a look at something which is like a synthetic key. Now, a synthetic key, you can concatenate, right? As we mentioned, you can take a tenant ID, you can take a user ID. It has higher cardinality. So basically what we're doing here is my placement hint is then the hash of the tenant ID and the user ID. So the Cosmos DB engine then basically has a hash of both these two values. Now, again, this is good to start with. I can write more than 20 GB of data per tenant, but we now have a trade-off, where the queries by the tenant ID are always cross-partition. Because what happens is, in Cosmos, in the engine cannot pass basically specifically the tenant ID from this full value, because it's basically a hash of both, right? And we only route queries to those physical partitions. So what you end up doing is you do a lot of cross-partition queries. In simple time, every time you query a specific tenant, you end up doing at the back end, basically doing a cross-partition query and querying all the underlying physical partitions. So it ends up technically becoming a full table scan. It's a poor way of handling queries. So maths-wise or growth-wise, scale-wise, it's not optimized for. And definitely it's not, it also adds very complex like application and query complexity, right? So it's something which you see looks good initially to start with, but then can't scale. So definitely you should look at something in a case like this, what we call the hierarchical partition key. So this is a very good fit for a hierarchical partition key. Why? Because we can set the partition key to tenant ID, then user ID. For us, here it suffices to have 2 levels. If you have a more nested use case, you can go to a 3rd level. So if you believe a combination of a single tenant ID and user ID will exceed like something like 20 GB, then we could use something like third party level as well. So what happens, an important point to note here is the placement hint then becomes a hash of the tenant ID plus we concatenate it with the hash of the user ID. And if you have an optional 3rd hash also, we concatenate with that. So technically, we concatenate these 2 hash value. Let's say I'm taking just the tenant ID and the user ID. And the resultant concatenation then becomes my placement hint in the DB. So it's highly scalable in nature. So this allows that I have more than 20 GB of data for a single tenant, and my system can handle adding more partitions as well. So all my, and of course in a particular hierarchical partition key query, if you mention both the 2 different let's say the tenant ID and the user ID, then it's 100% scoped in partition query. As a result, it's now possible for a single tenant of data to span multiple physical partitions. Yes, I can scope precisely to a particular physical partition as well. So it's a very good use case to optimize for if you have a case like this, specifically for multi-tenancy situations. That's what this particular problem kind of provides a solution for. So this is something which I wanted to kind of cover, and this brings me an end to our discussion.
Yep, thanks, Subhashish. I know that there is some network glitch in terms of the viewers seeing the slides because there was some delay, but I hope all of you were able to get what Subhashish was talking about. Yeah, I think you covered a lot of aspects on partitioning, starting from fundamentals to how we implement on our side, and also from the customer side, what are the best practices, and you covered some of the use cases, right? There is one more question on the chat. Let me take it up. Will there be a need for queries that span multiple partitions? How will cross-partition queries be handled efficiently? So the question is more on the guidance on how to handle cross-partition queries.
Yeah, so one very important point to note here is that when I fire cross-partition queries, they're ideally not evil in nature. That's very important. There will be certain scenarios and use cases where I may have the requirement of firing cross-partition queries. So I will, of course, there will be a need for queries that span multiple partitions. I've seen that many cases. Like a perfect example is I'm optimizing for game, but I have a particular query where it's player ID I have a requirement for. But that's like sub-minimal part of it, right? So there will be a need for queries that can span multiple partitions. There will always be a case. I've never seen a use case where it's 100% only scoped to all physical partitions they're looking for. But then, in such a case, there are multiple ways to handle efficiently. So a good way it would be to look at, can I first of all optimize it for, let's say, distribution? Can I look at, can I use different parallel combination factors that we have for the SDKs? You have in Java as well as in .NET. So that when the result and output comes through, I can handle it, paginate it, and I can improve the result and output. Or what I can see is if I have a scale of less than 5 to 10% in a given use case, then I can do different optimizations of the app layer itself only for the performance benefit. But if my use case becomes more than 20% or 30%, that's our good scale to look at. Then ideally speaking, you should apply a CQRS pattern. That's what we always do and optimize for in retail. That means I take that particular use case, I take that particular set of queries, I take that particular properties within my JSON, create a new container out of it and scope that particular, let's say a logical partition specifically for that particular set of queries. You will find the cost is always better, performance is 100 times improved, and your overall performance will be much better on the application. So that's a good way to look at it.
Yep, thanks. I think you answered it in the right manner. Yeah, there are certain considerations that we have documented, and also you can go through the links that we shared already. With that, we have come to the end of the sessions. Probably this is the longest and also, most useful session, I hope, because we got some interactions as well as we see that a lot of viewers have joined. Yeah, thanks everyone for joining in, and thanks Subhashish for your time and also sharing these valuable insights. We will meet again soon, and have a good day, everyone.
Thanks. Take care and bye.